Good morning, students. Let's discuss today a very important topic in the magnetism, and it was a concept usually or most of the times asked in the NEET and JEE and even JEE Advanced. So we try to today understand the motion of a charged particle in a magnetic field. If a uniform magnetic field is present in a space and you be projected a charged particle, then how it will move, what is its motion. So we will understand that concept in a detailed way, and we will solve even couple of questions based on that concept. So let's understand that motion of a charged particle in a uniform magnetic field. So if you're taking maybe the magnetic field here inward, this represents the inward magnetic field, or if I am representing this is outward magnetic field. Let's say the field strength here I'm considering B bar as a inward magnetic field in this region. Let's say I'm considering in this region the field strength B bar as a magnetic field into this board. Now what I'm doing is, after considering that field into the board, now we are taking a small is a charged particle. Let's say it's a positive charged particle I'm considering. Say let's take a charged particle Q. So as I'm taking a charged particle Q here, and I am giving the charged particle with certain velocity, say V bar. I'm projecting the charged particle with certain velocity V bar into the magnetic field. So automatically what will happen, once the charged particle which is having a velocity V bar vector entered into this magnetic field of B bar, so it experiences a force. So it maybe goes like this or it maybe goes like this. So it experiences a force. Because of that force, it will change its course of path. As we see in this diagram, once it is there, it experiences a force. The force will be in this direction. And the charged particle experiencing a force, and it started moving along this curved path. So then how we are going to quantify that force, in the sense the magnitude of the force, if we quantifying it, the magnitude of the force F bar could be equal to Q into V bar cross B bar. The magnitude of the force is going to be F bar equal to Q into V bar cross B bar. So this is the magnitude of the force acted on a charged particle when it is in the magnetic field. If the charged particle is moving in the magnetic field and the field is uniform, then what is the magnitude, what is the force? The force vector is going to be, in the sense, it's a Q into V bar cross B bar. Now let me make you understand the simulation. If it is a positive charge and negative charge, and if it's a magnetic field, how it is going to be varying. I will make you a simulation and understand it, and let's understand it with the simulation. Okay. So as we discussed here is, it's a points represents the magnetic field. Here the points represents the magnetic field. Say if I am taking that magnetic field here, what we are doing, outward we are taking. If I want to make it in inward magnetic field also, we can take. So let's say here a magnetic field strength of 2.1 Tesla. Let's say here a magnetic field strength of 2.1 Tesla or 2 Tesla magnetic field strength we are taking, and we kept in this space a magnetic field where magnetic field lines are into the board. Now what I am doing, a charge of positive charge of plus 5 coulombs, 10 power minus 16, in instance 5 into 10 power minus 16 coulombs, a positive charge I taken, and I am giving the charge particle of 8 into 10 power 6 meter per second speed. Let's say I am taking 8 into 10 power 6 meter per second speed a particle I am giving, and its mass is 8.4 into 10 power minus 25 kgs. So with these parameters, I am taking a charge particle. Now I am just projecting the charge particle into this magnetic field. Let's say if I am projecting this charge particle into this magnetic field, what we expected is, as per the formulas, it is going to experience some force and it is changing its path. What we expecting is, it is going to experience some force and it changes its path automatically. Instead of going in a straight line, it will experience a force and it will started moving in a curved path. So let's simulate that. If you look at it, let's see the simulation. If I projected a particle, let's see. So it has to supposed to go in a straight line, but once it is entered into the magnetic field, it has started experiencing a force. So if we project that particle, we can see here, it is going a straight line here because there is no force, the charge particle q, whatever the q, is moving in the straight line, but once it is entered into this magnetic field region, it start experiencing a force. So automatically it start moving in a different direction. How the force is going to be in the sense, see, the force vector could be F bar could be equal to q into V bar cross B bar. So this is what the magnetic force acting on the charge particle when it is enter into a magnetic field. Now, how you are going to determine its direction is also matters. Let's understand its direction. So the magnitude F bar equal to Q into V bar cross B bar, that's how you can calculate. So you can see that whether it is a positive charge in one direction, you can see here also, if it's a positive charge, it's one direction. If it is a negative charge, it's another direction. So positive charge particle experiencing a force and going this way, whereas negative charge particle will experience a force in this way. So it depends on the sign of the charge, whether it is a positive or negative. Based on that, the force may be in one direction or other direction. It depends on the sign of the charge too. And even here it is the force is depends on the what is the speed of the particle, and even what is the magnetic field strength of the particle, magnetic field strength in that region. On these parameters, the magnetic force of this charge particle will depends. Now, what is the direction, in which direction the particle will experience the force? So to talk about the direction, its direction, the force is going to be F bar equal to Q into V bar cross B bar. So one standard way of making it is the Fleming's left hand rule. What is the Fleming's left hand rule, or how you are going to talk about the Fleming's left hand rule is, what is the Fleming's left hand rule? Fleming's left hand principle or rule. So what is the Fleming's left hand rule in the sense, if you look at it, if you look at the charged particle's motion, you keep your fingers like this, such a way that keep this finger in the direction of magnetic field. Keep this finger in the direction of magnetic field and keep the middle finger in the direction of velocity. Keep this middle finger in the direction of velocity. Then automatically it gives, the thumb gives you the direction of force experienced by the particle. So what is the Fleming's left hand rule is, see, in this scenario, keep your forefinger in the direction of magnetic field and keep your middle finger in the direction of motion of the particle or velocity direction. Then automatically the thumb gives you the direction of the force experienced by this charged particle. So if we take here in this situation, let's take here in this situation, if the particle is here, let's say it is going in this direction, then V bar I am keeping, magnetic field I have to keep this way because it is into the paper, and this middle finger should be in the direction of what? V bar. Automatically then thumb gives you the direction of what? Force. So this particle will experience a force in this direction. This particle will experience a force in this direction. If it is a negative charge particle, then it will be experience a force in the opposite direction to that. So to determine the direction of the force, to determine the direction of this force vector, it's simple. We just need to apply the Fleming's left hand rule, where you have to keep your forefinger in the direction of magnetic field and middle finger in the direction of velocity of the particle, and force, automatically thumb gives you the direction of the force. Let's see here also you can check, if you're taking it is a positive charge, so your magnetic field in this direction, your velocity of the particle is in this direction, so upward direction thumb gives you the force direction. If it is a negative, automatically it will give you the opposite direction. Let's simulate that. If we can see that, we can simulate it. In this situation, let's take here, as we are taking a positive charge particle only, positive charge particle only, and we are projecting. So what will happen if you keep your forefinger into the magnetic field direction, into the paper, and as the particle is entering here in this direction, this way, as the particle is entering, so automatically thumb will give you the direction of the force. So the particle will go this way. So we can see that clearly. If it is enter, automatically it experiencing force everywhere, so it will go like that. If I am keeping a negative charge particle, if we are keeping a negative charge particle, see, let's take a negative charge particle. I'm just taking minus 4 into 10 power 6, minus 16 coulombs. So let's take I'm taking 10 power minus 16, minus 4 into negative charge particle I'm taking. So automatically what will happen? It will experience a force in the opposite direction to that, and it will go like that. So it depends even plus q or minus q, what charge you are taking. Based on that, you can apply the Fleming's left hand rule. you can apply the Fleming's left hand rule to determine the direction of the motion of this charged particle, I mean direction of the force experienced by this charged particle. Now, if you more elaborate on this, and what other parameters we can say, and or else what way, other way we can say it's a direction of charged particle or direction of the motion of this particle, in the sense F bar will be depends on Q into V bar cross B bar, and we know this is the vector quantity, and we know, as we know, this is the vector quantity. If you keep your, how we are going to determine the cross product V bar cross B bar, the direction of V bar cross B bar will be gives you what, simply direction of cross product itself is what, force direction, itself is a force direction. Direction of cross product itself is a force direction. So how you are going to determine the cross product direction, in the sense we are just keeping the right hand fingers in the direction of V bar and curling towards the B bar. So automatically thumb gives you the direction of force vector. So here if I am taking this, let's say this is the direction of the V bar, and what is the direction of V? Curl that towards the V, towards the B, V bar cross B bar. So thumb gives you the direction of force vector. So direction of cross product, simply right hand rule, you can apply right hand rule. You can apply to determine the direction of the force experienced by the charged particle. So to determine the magnitude of this charged particle, magnitude of the force on the charged particle, you can say simply F equal to Q into V bar cross B bar. Now to determine its direction, we can apply two rules. One is Fleming's left hand rule, or else right hand rule for the determining the cross product direction. So it's up to us, anything we can choose, and based on the situation of the question we can apply those two things. Now let's elaborate more on these things. Let's elaborate more on this. Now if you look at this, F bar could be equal to Q into V bar cross B bar. F bar could be equal to Q into V bar cross B bar. Now say, if I am taking, if the magnetic field is uniform, it means the B bar is constant. If I am taking uniform field, it means B bar is constant. Both ways, magnitude wise and direction wise, if B is constant, then what will happen? It depends on, see, if I am writing here Q into VB cross product, if I am writing sine theta, and let's say it's a perpendicular direction n cap, say it's F bar is that, your F bar vector. So what is this theta stands for here, in the sense the angle between the velocity vector, velocity of the charged particle and magnetic field, the angle between velocity vector and magnetic field vector. So now if the angle is different, say for example if the theta, the angle between velocity vector and is 0 degrees, or it may be 180 degrees. If it is a 0 degrees and 180 degrees, what could be the motion of the charged particle? Or if it is a theta equal to 90 degrees perpendicular, if the particle is projected perpendicular to this magnetic field, what will happen? Or else if theta is not equal to 0 or 180 or 90, then what could be the motion? Let's understand those things. Before going to that, first understand or visualize or else simulate that how a charged particle be in a magnetic field we can see in a 3-dimensional. Then we will come back to that and we will analyze these situations. So now what I am doing is, in the 3D, this is a 3-dimensional simulation for the magnetic field. So this is a 3-dimensional simulation for a charged particle motion in a magnetic field. So what I am doing is, see, we are taking a uniform magnetic field in a upward direction. Let's say in this direction, in this upward direction. Matlab, you completely have a uniform magnetic field in this direction. Let's say we are taking this way, or else let's see here, you can see this magnetic field is out to the paper. We can see this magnetic field is completely out to the paper, and this is your charged particle. This orange one is your charged particle, and this is completely, the magnetic field is completely, let me take it properly so that you can make it makes sense to you all. So this is how completely it's the magnetic field is out to the paper. Now if it is out to the paper, let's say I am taking, what we are doing is, the charge is just, we are taking that some 3 coulombs and all we are taking. Say mass of the particle is maximum we taken, charge q is we are taken, and velocity is in this direction, some particular velocity we are given. And now if you look at it, so what will happen? If you look at it, what will happen? Just see the simulation. So the charged particle will experience the force. And this is how it is continuously moving. let's say if I'm looking from the top view, this is what the field is continuously outward. If I'm looking from the side view, see the field is outward, so automatically if you pass it, so what you can understand here is same. What you can understand here, as this is magnetic field is outward direction, and this charge particle is moving this way. So automatically which direction the force is going to be? If I apply the Fleming's left hand rule, just apply the Fleming's left hand rule. So this finger has to be keep in the direction of the magnetic field, and this finger has to be keep in the direction of what? Speed. You're getting right? Speed. Automatically what will happen? The force is going to be this direction. The force is going to be this direction. Or else you can even apply this, we can apply even right hand rule. If velocity of the particle is this direction, magnetic field is this direction, so the force vector could be in this direction. So force vector could be in this direction. And this is what B bar is outward, and this is velocity vector. So automatically what will happen? Force vector could be in this direction. Wherever you take the particle, even if you take the particle here also, if the particle is here, it is moving this way, because since it is moving this way, the velocity vector is this, and magnetic field direction is this direction. So automatically force could be in this direction. You're getting right? This is a force vector, as since magnetic field is outward, and this is the velocity vector. So that's how you can determine the speed, velocity, direction of the force experienced by the charged particle in this. But here in this case, if you look at properly, observe carefully, what is the angle between V bar and B bar? What is the angle between B bar and B bar? V bar and B bar, the angle between them is going to be how much? The V bar and B bar, if you look at it, velocity vector is this, outward is the no. So this is the direction of the velocity vector, this is the direction of the magnetic field. Here also this is the direction of the velocity vector, this is the direction of the magnetic field. So everywhere if you look at it, the velocity vector and the magnetic field is 90 degrees, and that is the reason it's making a completely purely circular motion. Here if you look at it, if the velocity vector and B bar is making an angle 90 degrees in the sense, it is going to be what? Making a pure circular motion. Let's simulate it more so that you can understand. I'll just pass it. So we can simulate it more, and we can see, you can see that particle motion, how it is. And since the velocity vector and the B bar vector is 90 degrees angle, so it is making a pure circular motion in that way. Or else we can see in the 3D view, the 3-dimensional also. So all this is the magnetic field lines upward. And if you look at it, as the magnetic field lines are this way, and the particle is moving in this x plane, x direction, or this way, this plane x direction. So the particle motion and the magnetic field is making how much angle? 90 degrees. That is the reason it is making what? A circular motion. So what we can understand from this is simply, what you can understand from this, if the particle, the velocity of the particle and the B bar vectors are at an angle 90 degrees, the particle will make a circular motion in the uniform magnetic field because of the force experienced by the magnetic field. So if we mathematically quantify it, so here, so when theta is 90 degrees or when theta is 0 and 180 degrees, what you can understand, let's take, what you can understand is, see, if your B bar is this direction, and if the particle is also along the, if the particle is also in this direction having a velocity vector of charge q, then what could be the force experienced by that? Force experienced by that could be q into V bar cross B bar, where both are in the same direction, V and B. So theta is going to be what? If theta is 0 degrees, means V bar and B bar are parallel. V bar and B bar are parallel. Then what will happen to it? So automatically force becomes what? Force is going to be q into VB sin theta n cap, but theta is 0, so automatically the force is 0. It means that if the particle is projected along the magnetic field, it won't experience any force. If the particle is projected along the magnetic field, it won't experience any force. Similar way, this is the case when you take, even if the second case is also, B bar is in this direction and V bar, the particle's velocity is in the opposite direction to it, means theta is 180 degrees. Theta is also 180 degrees, then what will happen automatically? The force is going to be what? 0. Because VB sin theta is going to be 0 automatically. So what you can conclude from these two statements is, if velocity vector of the particle and B bar in the space are parallel or anti-parallel, parallel or anti-parallel, means theta is 0 degree or 180 degree, then then F bar is going to be force experienced by the charged particle is 0. So this is what you can understand. But if it is 90 degrees, what will happen? Say for example, if I am taking magnetic field this way. So third case we are taking, let's if it is theta is 90 degrees. As we already seen that simulation, so I can think you can understand that. So your B bar is this way, and we are projecting a charged particle of Q here, taking, and we are projecting like this, which is perpendicular. This means V bar is in the direction of I cap, let's say V I cap. B bar I am taking in the direction of what? J cap, B J cap, right? So both are perpendicular. I'm just taking theta is 90. What do you mean by theta is 90? In the sense both are perpendicular, and it's a charge is Q. So automatically what will be happen to the F bar? F bar equal to Q into V bar cross B bar. If you're taking that Q VB, I cross J is going to be how much better? I cross J is going to be K cap, right? K cap. So you will get force. So if you're taking this is how force going to be in this direction. That's how you can see it, right? So you can read this is not going to be 0. You have a maximum force F bar equal to QVB, and that is maximum. The force is maximum here. So once you see F equal to QVB when your V and B are perpendicular. When V and B are perpendicular, automatically your force is going to be what? Q into V into B, right? Now, and this is the maximum force the particle can experience when it is projected perpendicularly, and when it will be experience a 0 force and it will keep on its motion, in the sense it's just a, when it's a parallel or anti-parallel, V and B are parallel and anti-parallel, it is like that. Or when it is a perpendicular, the charged particle will experience a maximum force. Now, if already seen that, say okay, here it is experiencing a maximum force. In both cases, if you look at, as it is a perpendicular, it experiencing maximum force. When it is experiencing a maximum force, so you can see that it is making a circular motion. When the both are perpendicular, it is making a circular motion. Then we can see as it is moving in a circular motion, we understand from the circular motion or the Newton's laws of motions, there will be certain force will be that force which is actually the magnetic force. Here, because of the circular motion, we can consider it is like a centripetal force. So now when it is making a centripetal force and in circular motion, what is the radius of the circular motion? How you are going to determine the radius of the circular motion? So let's understand that radius of the circular motion. So what I mean to say is here, so as the charged particle is making a circular motion, now as it is going with the speed v, and it's a mass m, if the charged particle mass is m, and it's making a radius r, in the sense, what is this radius value? How I'm going to determine the radius value? Actually, how the centripetal force, so as it is in the circular motion, F is going to be how much? If I know the centripetal force Fc is going to be equal to m v square by r, right? The centripetal force is mv square by r. Based on this situation, the centripetal force, if its radius is r, in the sense mv square by r. But what is the centripetal force actually here? It is nothing but the magnetic force experienced by the charged particle. But what is the magnetic force? The magnetic force, if we calculate it, what is its value? The magnetic force Q into Vb. So in our conclusion, we can equate these two. Since this is the magnetic force which is causing this centripetal force, so it is making a circular motion. The centripetal force is mv squared by r, and so, and as well as if it is that force is simply because of what? The charged particle's speed, which is having speed v and moving in the magnetic field, which is experiencing that magnetic force, and these two are going to be equal. So let's do that. If theta is 90 degrees, the force experienced by this is going to be what? Q into V into B, right? The magnetic force, I can make it. And since it is moving in a circular motion, the charged particle is moving in a circular motion. Let's say it is, I'm taking just this way. This is, let's say, magnetic field. And the charged particle is making a circular motion since, and R, and the particle's speed is V. Right, the particle speed is v, and this is the b bar inside and outside, whatever you take in there. So automatically, what will happen to this? This is, if its radius is r, in the sense, and it's the charged particle mass is m, in the sense, what will happen to this? The force is going to be, and the centripetal force is going to be simply m v square by r, right? And we know that these two are going to be equal. We know that these two are going to be equal. Once we are equating the two, QVB equal to mv square by r. Since the two are equal, we can make it then r is going to be how much? The radius of this circular motion is going to be mvv is cancelled, mv divided by qb. So if you see this, the radius of this circle in the uniform magnetic field where the particle is making the circular motion, the radius of this circle will be depends on what? mv qb. Mass of the particle, speed of the particle, charge, and b also. It simply gives you what? Simply mv I can write as a momentum of the particle, qb, right? So this is also another relation we can keep. So just the radius, see, it means that what? If you want to increase the radius, either you can decrease the charge or magnetic field, or you can increase the mass or velocity. And this is very important relation. They can simply give you different parameters and they can ask you to compare these values. Say, let's see the simulation. If you can see the simulation here, say for example here, let's say if you look at this situation, I want to increase the radius. So what is the formula we have? Let's mark it the formula. So first of all, I will take these parameters and I'll start. Let's say some particle is projected and it will go into like this. Make it now positive charge. Make it a positive charge. So now see, this is how you have a charged particle going like that. So what is the radius in the sense? This is the radius is circular. Now if I am increasing to decrease the radius, what I need to do? Say for example, this is the radius of the particle. I have a mass, velocity, charge, and magnetic field. These are the 4 parameters. It depends: mass, velocity, charge, and magnetic field. If I want to decrease the radius, what I can do? If I want to decrease the radius, what I can do? If I increase the charge or if I increase the magnetic field, radius will decrease. What you can understand? If you increase the charge or if you increase the magnetic field, radius will decrease. Just understand that. Say if I increase the charge, say for example, I increase the charge. Now what will happen? Radius has to be decreased. Let's see that. Exactly, the radius is decreased. If I increase the charge, automatically what will happen, beta? The radius is decreased. Let's now, instead of increasing the charge, let's say increase the magnetic field. If I increase the magnetic field, let's say, if I increase the magnetic field, what will happen? Just understand this. See, the radius is decreased. Means you can understand this very carefully, that if you, as it is inversely proportional, if you decrease the charge or if you increase the charge or if you increase the magnetic field, radius will decrease. Similar way, if you increase the mass and if you increase the speed, the radius will increase. See, increase the speed, what will happen? The radius will increase. Let's see. Increase the speed, automatically, comparatively, what will happen? Increase the speed in the sense, comparatively, you can compare that. See, let's make it. Otherwise, first I'll keep this with this velocity and start. See, now see. This is what you have. Let's increase the speed and do it. So automatically it's happened like this. So increasing the speed further, if you increase the speed, automatically what will happen? Its speed is increasing. So increasing the speed will mv by qb. You can sense it all, mv by qb. So r equal to mv by qb, you can understand these things. So this is one important relation where they can keep a lot of questions on this, right? And so we understand if it is some other parameters, what you can derive is, see, what is its angular speed? If it's omega in the sense, if it is rotating, if it's making a circular motion with the angular speed of omega, what is the omega in the sense? Let's understand the time period also. How we are going to calculate the time period is, see, radius to mv by qb. Okay, fine. Then what is the time period in the sense? If it's a time period, could be 2 pi r by v. 2 pi r by v. So 2 pi r is nothing but how much, beta? mv by qb divided by v. So here vb is cancelled, 2 pi m by qb. So the time period of this charged particle which is moving in a uniform magnetic field, the time period is independent of the speed. It simply depends on the b and m, qbm. It simply depends on the qbm. So these parameters are important, these relations, when, and these are all valid only when the charged particle is moving with a 90 degrees. If it is, so just come back to this whole thing discussion. If the charged particle is moving along the magnetic field or parallel to the magnetic field, anti-parallel to the magnetic field, it won't experience any force. It will keep on going in the same direction. But if the charged particle is entering into the magnetic field in a perpendicular way, if the magnetic field is in this direction and charged particle enters perpendicularly, it experiences a force. And what is the magnitude of the force in the sense? It's a QVB. And this is the maximum force it experiences. And as it is entering into the perpendicular, it experiences a force and it creates a circular motion, and that circular motion would simply gives you the results of centripetal force itself. Like the circular motion is a result of centripetal force, so we can equate these two so that we can calculate even the radius of this path of this particle which is moving, and it's a time period. And we will continue in the next session. And if it is, what will happen if theta is not equal to 0 degrees or not equal to 180 degrees or not equal to 90 degrees, if it is projected in different angle. Just let me show you the simulation and I will explain this discussion in the coming session. So what will happen, what we'll do is, if the particle is not projected, if the particle is not projected 0 degrees, if it is also having with some different angle. So if the particle is not simply projected in perpendicularly, let's say it is having some angle along with the B. So the velocity vector is, say for example, this is a magnetic field vector. Earlier we taken the velocity vector is like this, which is making 90 degrees. But now let's say if it is projected like this, then what will happen to the particle of the path of the motion of this path? Let's see, this is what, if it is 90 degrees, just it is making a pure circular motion. Even if you look from the above, it is like this. But if I am giving some angle, so automatically what will happen? It makes an helical path, completely different kind of motion. So that is how it is going to be move when the particle is projected in some angle. It will have both components along the magnetic field and along the perpendicular to the magnetic field, and it comes clear to make a helical path as shown. So these things even mathematically we will continue in the next class.